This video is designed to review the equation sheet, to remind you what equations are on here, what equations aren't on here, what units should be used for certain equations, and in what areas equations apply and when they don't. So we're going to get going. I've got the equation sheet here. You can see that I've split it up in places where I'm going to write extra things, but this is essentially your equation sheet. So first we have these constants. Let's talk about them. Mainly what I want to talk about here is which constants you have not used. So you have not used this one. Okay, that's really thin. Let's make a thicker. Is that pretty thick? Awesome. So you've not used this one. Make it a little thinner so you can still see it kind of. Yeah, so we've not used that one. This second one here, that's the speed of light in meters per second. This is E, you haven't used it. Epsilon you have not used. H, that's Planck's constant. We'll talk about where we use that later. This one will come up in equations we've talked about. We really haven't used it. So I'm actually just going to go like this so I can reference it later. Ke we have not used. This here is the mass of an electron, the mass of a neutron, and the mass of a proton. Those are all valid equation or valid constants. Na, that's Avogadro's number, 6.022 times 10 to the 23rd. So I think a lot of you know that off the top of your head, but it is on the equation sheet just in case. And it's 1 over moles, meaning it's things per mole, right? It's anything per mole. Usually we're talking about atoms or molecules, but a mole is really could be anything. All right, this next one here, this is the ideal gas constant. Okay, these are the two that we've used, and this one we have not. Okay, they're all the same constant, just in different units. And so they're just provided for you here so that you don't have to do all the conversions, you can just use whichever one applies. And again, when we get to those equations, we'll talk about which ones apply. And then lastly here we have, this is Ridburg's constant, and again, we'll reference that when we get there. All right, then we have lengths, conversions, we have mass conversions, we have volume conversions, pressure conversions. One thing to be aware of here, right, if 1 atmosphere equals 760 torr and 1 atmosphere equals this, then you could also say that 760 torr equals 101.325 pascals, right, because they're both equal to 1 atmosphere. So that's good to know. If there's a little asterisk, that means those are exact values. So really 760 is not 2 sig figs, it's infinite sig figs because it's an exact value. But that doesn't really matter for you guys as this final is multiple choice. All right, so there's pressure. Then we have force. We really did not talk much about force. We didn't talk about power. And then we have energy. Okay, so there are your constants and your conversions. So now let's get into the meat of this, which is formulas. All right, this first one says density, right? Often we write density as a D, right? But this is written as a rho, which is like a Latin P. So we have this rho, density equals mass over volume. Okay, the units don't really matter there. It's just whatever units you pick for your mass and your volume will give you the units of your density. So if I pick mass in grams and volume per liter, I'll get grams per liter as my density. One note, grams per milliliter is a common density. Water, your density equals 1 gram per milliliter, which is why you might have converted between grams and milliliters and just used the same number, right? Now that's only true for water. Other things have different densities, and so this 1 gram is not the same as 1 milliliter, but that's true for water. All right, next we have the temperature conversions. Now, most of you are familiar with converting Celsius to Kelvin. That's right here. This is saying you take your Celsius, you multiply it by 1 over 1, so don't do anything, pretty much, and then you add 273.15, or 273, and that gives you your temperature in Kelvin. Okay. are familiar with that. Fahrenheit's a little bit different. You take your Celsius, you multiply it. Excuse me. You multiply it by 9 over 5, right? So this is just multiplying by 9 over 5, and then you add 32, which means if you're going, if you had your temperature in Fahrenheit, you could subtract 32, and then you'd multiply it by 5 over 9 to get your temperature in Celsius, if you're going from Fahrenheit to Celsius. All right, next we have our light equations. So here, this is the, let's see how I want to break this up. Yeah, okay, so here we have, I'm just going to do this. This is for light, or for photons. Okay, this is the speed of light, okay, which again is a constant given up here. There's your C value. And that C value is in meters per second, equals my wavelength, and wavelength is a length, so it's going to be in meters, times my frequency, which is in 1 over seconds, okay, because frequency is how often something happens per second. Okay, so one thing to be aware of here, often your wavelength is given to you in nanometers, not in meters, and so you would want to convert that. The other thing to be aware of is this 1 over seconds is also often can be written as s to the negative 1, right? Anything to the negative 1 is just 1 over that thing. So s to the negative 1, and it can also be written as hertz. That's the name of the unit 1 over seconds. All right, so then we come here and we have energy. Now energy is in joules, equals, so this is the energy of one photon, equals Planck's constant, which is h, which is 6.626 times 10 to the negative 34, joules times seconds. Okay, so that's joules times seconds, and then this again is my frequency, which is 1 over seconds. So you see there, your seconds cancels, right? And so you're left joules equals joules. Perfect. And so there's the energy of a photon. Now, one useful equation that isn't on here that people like to use is they like to calculate energy in relation to wavelength. So essentially, if we were to take this here and solve for wavelength, you get wavelength equals c over frequency. And so now I can replace, we're going to solve for frequency equals c over wavelength. And then we're going to plug that in right there, and you get energy equals h times c over wavelength, also written as hc over lambda. Okay, so that's how we can relate energy to wavelength. So we can see here that if frequency goes up, energy goes up. If wavelength goes up, energy goes down. Okay, so important correlations to understand. Okay, this brings us here. This is the de Broglie wavelength. Okay, so while these up here are wavelengths and frequencies and stuff of photons, okay, this here is the wavelength of something with mass. Okay, and so that's what we have here. We have the wavelength, which is going to be in meters because it's a length, equals Planck's constant, same one as before, and that's in units of joules times seconds, over mass times velocity. So you can see here the V's are a little bit different. Okay, this is the frequency, okay, but this is the velocity. And a good rule of thumb, anytime you have this V with an M, it's going to be velocity, not frequency. So you got your mass, and your mass is going to be in kilograms. We'll talk about why in a second. And then you have your velocity, which is in meters per second. So let's talk about why this works. I'm going to rewrite my joules. If I come up here, it tells me 1 joule is 1 kilogram meter squared per second squared. So I'm going to replace it, my joules, with kilogram meter squared per second squared. Then I have my seconds, then my kilogram, then my meters per second. Okay, so let's see. Let's cancel some stuff out. So kilograms on the top and on the bottom, so those cancel. Then I have seconds here on top, and this seconds, which is on the bottom of the bottom, which is like being on the top. And those are going to cancel out this, because being on the bottom of the top is like being on the bottom. And then I've got meters squared on top and meters on bottom, so we cancel out one of those. and then we're left with just meters. If that didn't make sense, I'm going to do it one more time, a little bit differently. So I'm going to have my joules is kilogram meters squared per second squared. Then I have seconds on top. I have kilogram on bottom. Then I have meters per second on bottom, which flips and becomes second per meter. Because on the bottom it flips. So then I cancel second and second with seconds, kilogram with kilogram, and one of my meters with that one, and I'm left with meters, which is what I want. Again, so that is the wavelength of something with mass. Okay, this is the general equation for kinetic energy. Kinetic energy, which is going to be in joules, is 1/2 mass, which is in kilograms. I'll write it. Mass, which is in kilograms, and then velocity is in meters per second. So you can see when we square that meters per second, we're going to get kilograms meters squared per second squared, which again we said up here, kilogram meter squared per second squared is the definition of joule. So. Perfect. And we'll talk about where that comes in later. All right, E equals mc squared. That's great. You've probably heard of that equation before, but we did not use it. This is work function. So if you remember, work function has to do with having a piece of metal, shining a photon on that metal, and kicking off an electron. So we kind of have the energies of three different things. We have the energy of the photon. Okay, and energy of photon is equal to h nu. And we know that because right here, energy is equal to h nu. So we have the energy of the photon. Then we have the work function right here. The work function, which is kind of like the energy of the metal, is the minimum energy to eject, minimum energy a photon needs to kick off an electron. And then here, this electron has kinetic energy. All right, so basically what we're saying here, and I'm going to write this equation a little bit different, we're saying that the energy of your photon comes in, that energy can go to two places. First, it goes to the work function to kick off or to remove an electron. And then if the h nu is bigger than the work function, all of the rest of the energy goes into kinetic energy of the electron. You can see the way I've written it is the same as here. It's just in this case they subtracted kinetic energy over. So here, work function is going to be in joules. H nu, H is in joules times seconds, and nu is 1/seconds. And kinetic energy of the electron is going to be joules, which makes sense. Seconds cancels out. We got joules equals joules plus joules. Okay, and then maybe you can solve, if you solve for the kinetic energy, you can then use this. This is the same kinetic energy, okay, and 1/2 mv squared. So this is kinetic energy of an electron. So then, because I know the mass of an electron, which is up here, mass of an electron, I can then find, because if I found the kinetic energy, that's that. If I had the mass, I could find the velocity of that electron. All right, here, this is the energy of an n level. So remember, with Bohr's model of the atom, we have our nucleus, then we have, different rings. This is like n equals 1, n equals 2, n equals 3. Okay, if we just want the energy of one of those n levels, that's this guy right here. So let's talk about what each of these are. Z is the atomic number. Now, we only have really ever done this for hydrogen, and so as a result, Z is always 1, and 1 squared is 1, and so Z kind of goes away. So you might not be familiar with it because you never had to put anything there. Okay, then we have some constants, RH, H, and C. Up here, you see we have RH, H, and C. Okay, so they're all just given to you. Okay, and then we have n squared, and that n is literally the n level that you care about. Wow, my pen's going wacky today. It's the n level you care about. So if I'm trying to find the energy of n equals 2, I'm going to put in 2 in the bottom there. Let's check the units. So RH is in units of 1/meters. Okay, so I've energy should be in joules. Okay, my RH is 1 over meters, my H is joules times seconds, and my C is meters per second. Let me write that in red for consistency. Joules equals 1 over meters times joules times seconds is H times meters per second. So we get meters canceling and we get seconds canceling. We're left with joules, which is what we want. All right, here we have, this is the uncertainty equation. The uncertainty equation has to do with the fact that with very, very small objects like electrons, we can never know where they are and how fast they're moving simultaneously. Okay, so we can, the more certain we become in one, the more uncertain we become in the other. So that's what's shown here. It's basically saying the uncertainty in the position times the uncertainty in the momentum has to be greater than or equal to this quantity h over 4 pi, which means if I become more certain in x in its position, so if my uncertainty in the position goes down, in order to keep this inequality true, the uncertainty in the momentum has to go up. When we use this equation, right, we know the mass of the particles we're talking about, so we end up with delta x times mass times delta velocity is greater than or equal to h over 4 pi. Okay, so the uncertainty in my mass, or in my position, that's going to be in meters, because it's a position. The uncertainty in my mass, I shouldn't say uncertainty, excuse me. The mass is going to be in kilograms, and the uncertainty in the velocity is going to be in meters per second. And that all has to be greater than or equal to h, which remember is joules times seconds, but I'm going to rewrite it because joules is kilogram meters squared per second squared. So that's joules times seconds means I need to add another seconds. So let's see if this works. Seconds cancels with one of those, and then I'm good. I've got kilogram meter squared per second, kilogram meter squared per second. So the units work out. And that's why it's important that our mass should be in kilograms, because on the other side of the equation we've got joules, which has kilograms in it. So our mass should be in kilograms. Okay, this is the Ridburg equation. Okay, really I think that this should be written after this one, because basically this is the energy of an n level. If I were to want to find the difference in energy between two n levels, I would find the energy of one n level and subtract the energy of the other. Okay, and that's what this equation is doing. It's just doing that, and then it's solving for wavelength instead of energy. Okay, so this is to find the wavelength, but if we have two n levels, and we fall from one of the n levels to the other, that falling is going to emit a photon. That photon is going to have a wavelength. That's what this equation calculates. So if I pick one of my n's and then my other n, then this is the Ridburg constant, which again is given here, Ridburg. This constant. That will give me 1 over the wavelength. And the units make sense because n's are unitless. Ridburg's constant is 1 over m, and this would be 1 over m for the wavelength. 1 over the wavelength, which would be 1 over m. Now a lot of people wonder which n goes first. Do I put final minus initial or smaller minus bigger? I always tell my students, don't worry about it. Just plug in your n's, because at the end of the day, if you plug in the wrong ones, it's just going to flip the sign. Like if you flip the n's, it's just going to flip the sign on your answer. And so you need to think about what your answer should be. So if I'm solving for a wavelength, that should be positive, right? It's a length. If I'm solving for a frequency, that should be positive. If I'm solving for the energy of this photon, so in other words, I get the wavelength and then I'm going to convert it to energy, well, a photon has to have positive energy. The time it can be negative is I'm finding the change in energy of this electron. Right? If this electron is going down, it's losing energy in the form of a photon, so that would be negative. Right? But if an electron was going up, that can only happen if it absorbed a photon, so that electron would be gaining energy, so that would be positive. So a change in energy can be positive or negative, but a wavelength, the frequency, or the energy of a photon is always going to be positive. All right, that brings us to this guy. You did not ever use this one, so don't worry about it. This is Coulombs' law. Oops. Coulombs' law. Don't know if I spelled that right. That's okay. Coulombs' law. And Coulombs' law says that the force of attraction between two things is proportional, or I guess in this case is equal to this value. That's a constant, which is up here on your equation sheet. It's the one. Did I cross out the wrong one? I did. So what I should have done is cross out that one and just X out that one. So this Ke, that's the constant for this equation. But again, you're never doing math with this. It's just conceptual. But if you really wanted to do math, how'd that happen? And so what we get is Ke times, this is the charge of one particle, this is the charge of another particle, and this is the distance between them squared. Okay, so you never did math, so I'm actually going to cross it out because you never did math with it. But I'm going to cross it out in a smaller ink. But you should understand that if I have two charged particles, if I increase the charge, I'll increase the force of attraction between them. If I increase the distance between them, I'll decrease the force of attraction between them. Okay, those are the correlations you should understand. It looks like I have that thing posted, but I have it posted again there, so I'm going to quickly get rid of that because it's not supposed to be there. Too big. Just going for consistency. Okay. So that's Coulombs' law. Again, you won't do math, you just need to understand conceptually. All right, that brings us up here. This we never used. This here is that the total change in energy of the system, energy can change in two ways, heat and work. Okay, so this is change in energy, which would be joules, which means this needs to be joules, and this needs to be joules. And I'll label them, this is heat, and that's work, and this is internal energy. Then we have, and let me reference another equation as I'm doing this. You see right here, here's our equation for work. So I'm actually going to draw an arrow to connect these two. Okay, work is negative P delta V, which means that my change in energy is going to equal to Q minus P delta V. Right, because I just replaced work with its equation negative P delta V. Now this brings up an interesting issue because we look at the units, energy is joules, heat is joules, work should be joules, but pressure times change in volume would give us atmospheres times liters. Okay, and we need this in joules. Fortunately, our equation sheet helps us out because it tells us here 1 liter atmosphere is 101.3 joules. Okay, and so we would have to use that conversion if we're solving for work with P delta V. We'll get liter atmospheres, and we'll have to change it to joules before we can plug it in here. All right, this next one, this is the first law of thermodynamics. It says the total energy of the universe does not change. Or energy can't be created or destroyed. The total change in the energy of the universe is 0. So energy can just be transferred from one form to another or from one thing to another, but it's never created or lost. This is the second law of thermodynamics. Which is that the total change in entropy of the universe is always increasing. It's greater than or equal to 0. Okay, and I'm going to add for spontaneous process. Okay, but spontaneous processes are things that happen. So for all things that happen, they must be spontaneous. So the delta S of the universe must be greater than 0 for each of those processes. So the total the total delta S of the universe will always be increasing. That's the second law of thermodynamics. Now, that's not saying that delta S is greater than 0, or is always greater than 0. Okay, that's not true. Right? Because we definitely have processes where entropy goes down. Right? Like if you freeze water, you are reducing the amount of disorder in that water. Okay? But that's because that's entropy of the system. This is saying entropy of the universe has to be greater than 0 for something to happen. Okay, not entropy of the system. All right, this is how we calculate entropy. S equals KB times ln W. And that is, I guess I'll just X this one out too. That's this guy. KB is Boltzmann's constant, which again is given right there. W is number of microstates. Number of ways that something can be arranged. That's a microstate. So that's how you would actually calculate the entropy of something, but I don't think you ever did that. Okay, what is important to know is the third law of thermodynamics says that entropy equals 0 for a pure crystal at 0 Kelvin. That's because a pure crystal means everything is aligned exactly as it should be, and 0 Kelvin means everything is at its absolute minimum level of molecular motion. So energy can't be exchanged between molecules. The reason entropy is 0 for that is because a pure crystal at 0 Kelvin only has one way to be arranged. Right? There's no disorder in it at all. It's exactly the way it should be. And so because of that, the number of microstates is 1, and ln of 1 equals 0. And that's why we get an entropy of 0. Okay, so that would be important to understand from this equation, even though you'll never do math with this equation. Okay, that brings us here. Q equals mc delta T. This is to find the heat required to change something's temperature. Okay, so the heat required, so this is going to be joules, is going to equal the mass, which is grams, times the specific heat capacity, which is usually in joules per gram times degrees Celsius, times change in temperature, which is going to be degrees Celsius. And you can see there the units work out. Grams cancels grams, Celsius cancels Celsius, and I get joules equals joules. Some things to be aware of. Because this is a change in temperature, because it's a change in temperature, degrees Celsius is the same. Excuse me. The change in temperature, degrees Celsius is the same as Kelvin. What I mean by that is, let's say that I'm changing from 0 degrees to 10 degrees. So final minus initial, 10 minus 0. That's in Celsius. If I were to change that to Kelvin, it would be 10 plus 273 is 283. 0 plus 273 is 273. And you can see both of those equal 10. And so sometimes you'll get this heat capacity given in like joules per gram Kelvin. It's okay to leave the change in temperature in degrees Celsius. You could change it to Kelvin if you want, but as long as it's a change in temperature, Celsius and Kelvin behave the same. All right, another thing to be aware of here, let's say they give you your C value in joules per mole degrees Celsius. Well, then you shouldn't multiply by mass, right? You should multiply by moles of your stuff and degrees Celsius to give you joules. Now, the other thing is with a calorimeter, which is just an object, you can't have a certain amount of moles or grams of a calorimeter. It's just a box, a bomb calorimeter. And so they kind of take these two and multiply them together for you, and they give you a C value in units of joules per degree Celsius. So then to get joules, you are just going to multiply by degrees Celsius. So again, just pay attention to your units. You're trying to get Q, which is heat, which is going to be in joules, or kilojoules, of course. So this is to find the heat when you're just changing the temperature of something. If you want to find the heat when you're not changing the temperature, which would be heat of a reaction or phase change, this is not given on your equation sheet, but you would have Q equals N delta H. And I'll actually write it in black because it's an equation, which delta H is basically just saying how much heat do I get from each mole that goes through this process, right? So if I'm vaporizing, this will be delta H of vaporization. If I'm combusting, it'll be delta H of combustion, right? So kilojoules per mole. So then I have to multiply by moles to get my kilojoules. And of course, if they give me kilojoules per gram, then I'm going to multiply by grams to get my kilojoules. Okay, so again, that's not on the equation sheet. It's N delta H. That's to find the heat change, or the heat required to do a reaction or a phase change, something where heat's being added but temperature's not changing. Because if temperature's changing, we're going to use an MCAT. All right, we talked about work. Remember that work is going to be in joules. Well, I guess you could say this is going to be atmospheres, and you're multiplying by change in volume, which can be liters. So that means I get work as liter atmospheres from this equation. And then I would want to change that most of the time to joules, because I know using that conversion factor, which is given right here. And again, I would want to change it to joules, because if I want to plug it into this equation, energy is in joules and heat's in joules. Okay, that brings us to enthalpy. Enthalpy is equal to internal energy plus P delta V. Enthalpy is like the total energy in a system. So it takes into account the internal energy, which is like kinetic energy and potential energy, and adds on to that the energy that this gas, for example, has to exert in order to maintain its volume. So you could really say that H equals E plus PV. So then delta H equals delta E plus P delta V. And that's assuming, let me jump over here, plus PV. So delta H equals delta E plus delta PV, which is delta E plus P delta V plus V delta P. Okay, I should do delta P, V in parentheses. Assuming, though, that pressure is constant, because it is in Chem 105, this delta P is 0, so that term goes away. And that's how we get to this guy. So this is to calculate the change in enthalpy if you know the energy and the P delta V. So the other thing that's useful about this is that we know that energy, or delta E I should say, is Q minus P delta V. So I could replace this as delta H equals, delta E is Q minus P delta V, that's my delta E, and then plus P delta V. And you should notice my P delta V's cancel, and I'm left with delta H equals Q, which just means enthalpy, which normally consists of a bunch of different stuff, and it's kind of a complex thing to get your head around. Well, when pressure is constant, right, we made that assumption right here, pressure is constant, basically enthalpy simplifies to just referring to heat. Okay, and again, H is change in enthalpy is joules, change in energy is joules. This is pressure atmospheres times volume in liters, so I would have to change that to joules to make this work. All right, change in entropy. There's a couple ways to calculate change in entropy, right? Just like there's, well, yeah, let me back up real quick. How do we actually calculate the change in, is that on here? Oh, it is. Okay, so we're going to get there. So this is entropy, the disorder, the change in disorder. So for a reversible process, what is a reversible process? For you, that means a phase change, and it means when you're dealing with the surroundings. In other words, situations, surroundings. situations where you are adding heat to something but the temperature isn't changing, that's a reversible process, and that's when this equation, I should say, applies. So with a phase change, we know we're adding heat, but our temperature doesn't change, right? Because all that heat's going to break into molecular forces to change the phase. So we're adding heat, change temperature, or adding heat without changing temperature, so that applies. And then surroundings, right? If I burn a campfire, I release heat into the atmosphere, but it doesn't change the temperature of the atmosphere hardly at all. And so that's the case where I'm adding heat and the temperature is not changing. So again, those are called reversible processes. These are the two that you deal with in this course. And in that case, if you want to find the entropy change of something, you just take the total heat of that process divided by the temperature that process is happening at. So heat is joules, temperature is Kelvin, and entropy is joules per Kelvin. So that's set. The other way to calculate entropy is if I have the entropy values of everything in my reaction, I would just take the entropy value of my products minus the entropy value of my reactants. It's pretty much saying my entropy final minus my entropy initial is going to equal my change in entropy. Okay, that brings us to this equation for delta G. This is Gibbs free energy, so it's energy, so it's going to be in joules, H is going to be in joules, T is Kelvin, and entropy is joules per Kelvin. So the units work out. And we talked about how to calculate delta S. There's another way to calculate delta G, and that's if I have delta G of formations. So if I have delta G of formations for everything in my reaction, this is if you're calculating delta G at standard conditions, so 0 degrees Celsius. Wait, let me think. Sorry, 25 degrees Celsius. You can use the standard enthalpy of formation values if they're given to you by just doing products minus reactants. Okay, so this will only at 25 degrees Celsius, this at any temperature. Okay, so you would have to, if you want to find delta G at a given temperature, you would have to find the delta H of that process, which we'll talk about how to do that down here. Then you have to find delta S. We talked about two ways to do that, right? Q reversible over T, or products minus reactants. And then we can plug in our temperature and get our delta G. So two ways to calculate delta G. One at only 25 degrees Celsius, the other at any temperature. The other thing to note is one common problem is to say, what's the temperature at which this thing starts to happen, or what's the temperature at which this becomes spontaneous? Remember that delta G is positive for non-spontaneous and negative for spontaneous. So when something switches from being non-spontaneous to spontaneous, it switches from positive to negative, so delta G is equal to 0. And we call that being equilibrium. So if you're asked what's the temperature at which this process happens or begins to happen or becomes spontaneous, you would set delta G equal to 0, solve for your delta H for the process, delta S for the process, and then you could solve for T after you find your delta H and delta S by other means. All right, here we have an equation for delta G that is not used, so don't worry about that. And now we have a couple ways to calculate the delta H of a reaction. So up here you would need to calculate this delta H, and this is how you could do it. The first is that if you have delta H's of formation, you would do products minus reactants. Hopefully you're familiar with that. And then the second is if you had bond enthalpy. So if you were given like, oh, a CC bond has an enthalpy of, X kilojoules per mole, and a CH bond has a bond enthalpy of Y kilojoules per mole. If you were given those values, then you would look at, draw your Lewis structures and find all the bonds that are broken, and then you would add up all of the enthalpies of those and subtract the enthalpies of all the bonds that are formed. Okay, so that's like saying reactants, because the reactants are broken, minus products, because products are formed. Okay, so everything is products minus reactants, right? If I'm solving for delta G, products minus reactants. S, products minus reactants. H, using delta H as a formation, products minus reactants. But if I'm using bond enthalpies to find my H, I'm doing reactants minus products. That brings us to gases. So this is the ideal gas law. It says that pressure in atmospheres times volume in liters equals moles times R times temperature, which is in Kelvin. To make this work, we need an R value in liter times atmospheres over mole times Kelvin. Unfortunately, we have one of those given, right? R value right here. Liter atmospheres, moles, Kelvin. Okay, and so we're going to use this R value of 0.08206. So right here, this should be liter atmospheres per mole Kelvin. Okay, so if we're given 3 of these things, we can find the 4th. Another application of this equation is if we have a gas that's in one set of conditions and then gets transferred to a different set of conditions. And in that case, we have our first set of conditions. We know that PV over NT is always going to equal R. So it's going to equal R in the first set of conditions, and it's going to equal R in the second set of conditions. So PV over NT is always going to equal PV over NT. And then I can look at my problem and I can say, is there anything in this problem that isn't changing? Okay, when I move my gas from situation A to situation B, anything that's not changing, I can just erase, right? And then I'll have everything I need, plug in all but one of your values, and you can find the remaining value. So anyway, 2 ways to use the ideal gas law. One is just to find one value when they give you the other 3. The other is to treat gas in situation 1, moving to situation 2. And they say, oh, this and this and this change, what happens to this? Right? That brings us here. This is the partial pressure. Partial pressure, which basically says the total pressure in a system is going to be the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3. And the other thing to recognize is the partial pressure of a gas. So the pressure of gas 1 is equal to the total pressure times the mole fraction of gas 1. Okay, and the mole fraction is moles of 1 over total moles. In other words, if 50% of the moles in my gas are oxygen, then 50% of the total pressure is going to be the pressure of oxygen. Okay, so if I can find the mole fraction, I multiply that by the total pressure, and that gives me the partial pressure. Another way to write this, if this makes more sense, is to say the pressure fraction is the pressure of my gas over the total pressure is going to equal the moles of my gas over the total moles. That is partial pressure. Okay, here we have molecular weight of a gas. Because we've got a gas sample, we know some things about that sample, and we want to find the molecular weight. Well, this molecular weight we usually have in grams per mole. That's that big M. And that's going to equal the mass of my gas, which we usually have as grams. Then we'll have R, which we'll use the same R as before, so liter atmospheres per mole Kelvin. And then the temperature of the gas, which will be Kelvin, over pressure, which is pressure, which is atmospheres, and volume, which is liters. Okay, and again, I'll write here the R we're going to use is 0.08206 liter atmospheres per mole Kelvin. Same as the one we'll use for the ideal gas law. Okay, this is really just a derivation or an adaptation of the ideal gas law to solve for molar mass. And you can see here Kelvin cancels with Kelvin, liters with liters, atmospheres with atmospheres, and I'm left with grams over moles, which is what I want. Perfect. So if I were to use the mass as kilograms instead of grams, I would just get my molar mass in kilograms per mole. But since we usually like molar masses in grams per mole, because that's what's on the periodic table, it's best to use the mass in grams in this equation. Here's another adaptation of the ideal gas law, which is to solve for density. So I know that over here we said density is a little fancy P. Well, we're just inconsistent, and down here it's a D. So here the density, which is going to be grams per liter, is going to equal my pressure. Pressure is going to be in atmospheres, times my molar mass, which is grams per mole, over R, same R, liter atmospheres per mole, Kelvin, times temperature, which is Kelvin. So as we cancel, atmospheres cancels atmospheres, Kelvin cancels Kelvin, and moles cancels moles, and I'm left with grams over liters, which is a density. So that's the density of my gas. This is van der Waals equation, which is for non-ideal gas calculations. You can see this kind of has the form of P V equals nRT. So that's PV equals nRT, that's the ideal gas law. Okay, but then PV equals nRT, but now we're saying, well, maybe the pressure isn't exactly what you would expect it to be. And so we take the pressure and then we adjust it with this term. The reason pressure might not be what you expect it to be is because of the effect of intermolecular forces on things. And then we have maybe the volume isn't exactly, because one of the assumptions of ideal gases is that the volume of the particles is pretty much zero. Well, maybe it's not pretty much zero, and so we have this term to adjust for the volume issue. So A adjusts for pressure, B adjusts for volume, and A and B are constants that are dependent or that are based on whatever molecule you're dealing with, and so that's why they're not on the equation sheet, because they would just have to be given in a problem. So you would treat this just the same. Pressure is atmospheres, then you have A, and then you have N, which is moles over liters for volume, and that's squared. Okay. And then you're going to have, which means A is going to have some weird units of liters squared, like liters, let's see, atmospheres times liters squared over moles squared. But that'll just be given to you. So that's that. And then I'm going to have my volume, which is going to be liters minus N, which is moles, times B, which must be liters over moles. That's going to equal N, which is moles, times R, which is liter atmospheres per mole Kelvin, times T, which is Kelvin. And that leaves me with, this is atmospheres here, this is liters, and when everything cancels here, you get liter atmospheres. So the units work out. Then you'll be given A and B, and then you can solve for whatever else you need. Now you see N is in 3 different spots here. V is in 2 different spots here. So you probably won't be asked to solve for N or V, because mathematically you probably don't know how to do that. But pressure is the most common to be asked for. You could also be asked for temperature. Okay, so before I talk about this equation, I'm going to jump down and talk about this one. This is the root mean square speed of a gas. So basically we take the velocity of all the gas particles, we square them, we take the average of those squared values, and we take a square root of that. And for a gas, right, root mean square speed. For a gas, that comes out to 3RT over M. In this case, 3 is just value. R, in this case, we're going to use 8.314 joules per mole Kelvin. Okay, and that is right here, 8.314 joules per mole Kelvin. The reason we want to use that has to do with units. Okay, and then temperature is going to be in Kelvin, and mass we're actually going to do in kilograms. So let's look at it. Root mean square speed, it's a speed, so it's going to be meters per second. It's going to equal the square root of 3 times R, which is going to be joules per mole Kelvin, times temperature, which is Kelvin, over mass, we're going to use kilograms. Okay, and remember, I'm going to rewrite this, because remember joules, we're going to break down into kilogram meter squared per second squared, that's my joules, per mole Kelvin. So that's my value for R. Then my temperature is in Kelvin, and so my mass is going to be in kilograms. When I do that, Kelvin cancels Kelvin. Oh, mass. It's a molar mass, so it's going to be kilograms per mole. There we go. Kelvin cancels Kelvin, moles cancels moles, kilogram cancels kilograms, and I'm left with square root of meters squared per second squared, which is meters per second. Okay, so we got to use kilograms for mass here, and we got to use 8.314 joules per mole Kelvin. I should say kilograms per mole is molar mass. Gives us the root mean square speed of a gas. But if I wanted to know two gases related to each other, I would take the root mean square of A over the root mean square of B, which is going to be 3RT over the mass of A divided by 3RT over the mass of B, which is 3RT over the mass of A times the mass of B over 3RT, and my 3RTs all cancel, and I'm left with the mass of B over the mass of A. And that's what you see here, the rate or the speed of A over the speed of B equals the square root of the mass of B over the mass of A, and that rate could be a diffusion rate or a fusion rate or just a moving rate. Okay, and again, these masses, because we do a fraction, you could have it in grams per mole or kilograms per mole, it doesn't matter. And often you'll be given a rate as just, they'll just say like, oh, gas A moves twice as fast as gas B. Well, then I don't need to know either rate, because I know that gas A will always be twice as fast as gas B, so I'll just put a 2 and a 1. Or I could put a 4 and a 2, right? As long as A is twice as big as B, that will work out. Okay, so these two are very much interrelated. This is the kinetic energy, the average kinetic energy of a gas, and you likely never use that. Think of one situation where you could have, but you never needed to, and probably didn't talk about it much. And then these last two equations, these are for acids and bases, which we didn't talk about in this class, so those are gone. Okay, so there you have it. There is your equation sheet. Hopefully that's helpful in reminding you some of the things that you've learned, some of the things that you should remember because they're not on the equation sheet, and remind you of the application of some of these equations.